All right, everybody, welcome to e-learning day 5 with AP Calculus AB here at Avon High School with Mr. Meunier and myself. We're going to go ahead and talk about topic 8.4, the area between curves. We're going to hit 3 examples. We're going to be able to go through these fairly quickly. They're all kind of similar. And I believe that Mr. Meunier is going to take the lead on our very first example. So I will defer to him.
Okay, yeah. So if we're going to find the area between two curves, in essence, we're just finding, like we've done before, we're finding the area under a.
I'm not so sure. I don't hear you anymore, Mr. Meunier. Is it just me? Can anyone in the stream hear Mr. Meunier? You can type in the chat, yes or no. Okay. I'm going to try to shoot him a text, maybe. And if we can't bring him back online, I can go ahead and take over this one. I just don't want him to continue to teach if he knows that. But stand by for just a moment, everyone. All right, sorry, everybody, we're back. He just called me to say that he got kicked out of the Zoom session. So he's going to try to rejoin. But in the meantime, I'm going to go ahead and take over his example 1, and then we'll get back on track here in a second, you guys. But basically, if you remember a little bit about area under a curve or between a curve and the x-axis, we're just revisiting that idea. But we're just going to use a slight modification, and we're going to change that concept to that of finding the area of a region between two curves. As you can see in the diagram here, we've got a couple of curves, an f of x and a g of x. F is denoted by the blue function, g is the red function. And ultimately, our goal is to do what's going on really in this first picture, right? Finding the area of that pink shaded region. And we find out that to find that area, it's really nothing more than setting up a definite integral that certainly has boundaries, and those boundaries would be where you would think them to be, right? Your x values at which the shaded region is lying between. And then the change is what you see after the integral sign. We take the function f and then we subtract g. And I want you to always think of that function f as being the function that is on top. And therefore the function g is what's on the bottom. And it doesn't really take a whole lot of amazing insight to see why that works. Because if you just focus in the second picture of the region under the graph of f, then we would just integrate f of x from 1 to 3, and we would get this green region. But as you can see, that green region contains some stuff here with the question mark that I don't really want to include. So then if I think about finding the area under the red graph between 1 and 3, that would take care of this blue region here that I would end up subtracting away. And in this particular equation, green minus blue equals pink, right? So that's really all that's happening. It's just that we find it so much easier to consolidate the two functions within one integral and always separate them with a subtraction sign. Okay, so that's what's going on here. So if we go on to the box, box is just going to really reiterate what I just said. If you're going to find the area between f and g, notice how it says that g is less than, or at the very least equal to f of x, then we would always start with f of x first, right? It's always top minus bottom. Man, are you going to hear Mr. Meunier and I say that over and over again over the next several topics, okay? So for our first example, it says find the area of the region that are bounded by the graphs y equal x squared plus 2, y equal negative x equals 0, and x equal 1. And we do ask that you sketch the graph and shade the region. In all honesty, sketching the graph might be one of the most time-consuming components of this, and it's going to end up being a valuable resource later on when we start looking at more complicated applications like volume. So to sketch the graph, I'm going to use, let's say, a blue pen for the y equal x squared plus 2. So that means I can graph by placing a y-intercept here at 2. I can think about running a t-chart through this, letting x be 1. Well, then, of course, y is 3. If x is negative 1, y is also going to be 3. And I really can't graph a whole lot more than that. So there's our first function, y equal x squared plus 2. Next, I'll move on to a different color. I'll sketch the y equal negative x. Hopefully we're a little bit acquainted with him as a straight diagonal line with a slope of negative 1 that goes through the origin. Maybe looks something like that. Notice you don't have any enclosed region, not just yet. But if I throw in x equals 0, that'll start to happen because x equals 0 is going to be the y-axis here. And then if I finish up with x equal 1, I have this vertical line here at x equal 1. And then I can officially say that I have some enclosed shaded region. And I'm going to do a couple of things. I'm going to fix that last line. And then after I shade this, I'm going to turn it back over to Mr. Meunier because I believe he is back and he can talk about the integration setup for this.
Yeah, I'm back. Can you hear me?
Yep, we hear you good.
All righty. Yeah, the internet in the Meunier household just dropped. I had to reset everything.
Well, you got two teachers doing e-learning, so we're going to forgive you on that one. So
yeah. So with this, we got to find the area in yellow that Mr. Rector just highlighted. And I'm assuming you just talked about how he's got to do top minus bottom.
yes.
Yeah, so we need to integrate our boundaries along the x would be from the green line at x0. So lower bound of 0 to the purple line at x1, upper bound of 1. And it looks to me like we have our parabola in blue, x squared plus 2 on top. And we need to subtract our line in red of negative x on the bottom. So like Mr. Record was writing, x squared plus 2 minus negative x. This is with respect to the x-axis. It's dx. Maybe clean that up, 0 to 1. X squared plus 2 plus x dx. Then we have to integrate. So we're going to add and divide x cubed over 3 plus, add the variable on, 2x plus x squared over 2. We don't need a plus c. So we have the such that 1 on top, 0 on bottom. And then it just becomes a nasty arithmetic in some ways because you have some fractions. This one's not too bad though. Plug in the 1, 1/3 plus 2 plus 1/2, subtract, plug in 0. And what's that going to be? 2/6 plus 12/6 plus 3/6 gives us 17/6, I believe. I hope. I think that's it.
Yep, I think that's it. I think that's it.
The most difficult part, yeah, the most difficult part, I think, is just getting the picture, making sure you have your top and your bottom clear on these things.
Yeah, definitely agree. Definitely agree. The picture, obviously, you know, we're not suggesting. Let me get that out of the way. Let's, you know, using all the different colors. Yeah, hey, it's wonderful, but it's probably not practical for most of you. But I can't, and Mr. Meunier and I agree on this. We can't emphasize enough the importance of establishing this picture for when these problems start to get much more complicated later on. There also is a way that you can use the calculator to check these. We're going to probably hold off on showing you that until later in the week. Don't worry about that right now. We can't stop you if you want to use your calculator to check your definite integration, but we definitely want to make sure that you're able to handle these without the use of a calculator. I know that, you know, if and when we come back to school, obviously there are components to our exams that, you know, will not allow us to use the calculator. This could certainly be a non-calculator problem on the AP exam. So you definitely don't want to rely on the calculator too much at this point. All right, I think I'm going to go ahead and take over example 2, and then we'll let Mr. Meunier wrap it up with our example 3. And here it says, in this example, it says we're going to find the area of a region bounded by the graphs of f of x equal 2 minus
Hey,
x.
Mr. Record.
Yes,
We
I'm
had a
sorry.
question there. We
Oh,
had
okay.
a question about why we didn't. Yeah, want to read that?
Oh, yeah, Johannes, I didn't see that. I'm sorry. He asked,
Okay.
why didn't we use the x equals 0 and x equal 1 functions? Well, it turns out that we did. Those x equals 0 and x equal 1 functions served as our boundaries. So, and we have to be kind of careful because x equals 0 and x equal 1, they're not even functions, right? They're vertical lines. So a lot of times they're going to give you these other equations that you graph that don't get integrated necessarily, but just help serve as the left and the right boundary. So yeah, okay, yeah, it sounds like more than one of you had that question. So that's a very good point. And I think later on in this week, we're going to talk about these areas being oriented just a little bit differently so that we don't do top minus bottom, but we do a right minus left. But we've decided to kind of break that apart. In fact, I think that is tomorrow's lesson, in fact. So it's a very, very good question, you guys. So, all right. And hopefully we'll continue to see how that manifests itself even in this problem, because here you see just the two functions, f of x and g of x, but we don't see those two vertical x equal lines, and that probably means that we have a little bit different attack on this problem. So I'm going to go ahead and graph. I'm going to use the same color scheme. The very first curve I see, I'll graph in blue. And I might graph this a lot faster than what you guys are comfortable with. There is no contest for speed with this. If you have to set up a little T-chart off to the side, you're more than welcome to. You could do something along these lines. So if I let my left column be x, my right column be y, or how about we say f of x here. And we just start with some of the easiest x values to plug in, like 0. I get a f of x of 2. And if I let x be 1, I get an f of x of 1. And if I can go as high as 2, 2 minus 4 is negative 2, but that's about as much as I'm going to be able to sketch here, as you all can see. But lo and behold, I can graph probably negative 1 and negative 2 as my x values as well. And we see the nice symmetry that's being produced by this parabola that has a vertex up here at 0, 2. So if I connect all these guys, it's going to look something like this. All right. And then if I move on over to g of x equal x, that would be our good friend, the vertical, or the diagonal line, I should say, that now passes through the origin but has a slope of 1. All right. So I'm going to go ahead and shade this region in. And as you can see with this particular problem, there was something that was not provided that initially was provided in the previous problem. And that would be those boundaries of integration. Now, I'm sure that it's pretty easy to tell from the picture, right? Those boundaries of integration must be x values that depict where your shaded region begins and where your shaded region ends. And it looks pretty clearly like they're going to be negative 2 and 1, and that is right. In the event, let's say that you did not want to graph this, and I'm not saying that you have to graph to be able to find these areas. I've had many students in the past that would rather not graph it and have a pretty good understanding of which function lies on top, just based on their intuitive understanding of what an upside down parabola and a line like y equal x might look like. And what those students would have to do is off to the side, solve the two equations equal to each other. Right. Now, this is going to be a little overkill because it's certainly not necessary that I do this because I've already found those points of intersection. But I want to show this to you nonetheless in case you guys decide to take that approach. But it doesn't take a whole lot of effort. You're just talking about a little algebra 1 type of concept here, just to solve this simple quadratic equation. And you would see that x is -2 and x is +1, which indeed were those two boundaries. Okay. So at this point, we can say that our area is just simply the antiderivative from -2 to 1, right? The definite integral from -2 to +1. The top function looks like it's my 2 minus x squared, and the bottom function is my x. Notice that you definitely want to subtract those two, like I just did. And then the fun stuff begins. For space purposes, I'm going to go ahead and write this over here. So if I integrate 2, I will get 2x. Integrate x squared is x cubed over 3. Don't forget your minuses there. Integrate x, you get x squared over 2. And then the boundaries are 1 and -2. And you can see, maybe from the sound of my voice, a little part of me is dying here because this is very reminiscent, I think, of the beginning of your 8.1 assignment, which I know isn't fun, and I know you guys don't revel in having to do things like this, but we just want to make sure that you get these reps so that you don't miss simple problems that are multiple choice that involve a degree of simplification. So you're going to replace all these x's with 1. So I would get 2 minus 1/3 minus 1/2, right? Cubing 1 and squaring 1 is quite easy. Now, if I subtract the quantity of what happens when I plug in 2, this is going to be a little bit more interesting. -4, of course, leads off. Now, this negative that we have here, I think is going to be canceled with another negative because -2 cubed is -8. So double negative is a plus. So there's positive or +8/3. But yet this minus sign I think is going to stick around because -2 squared would be +4 divided by 2 is 2. Now at this point you could go ahead and you could get your common denominator of 6. You could also combine the like terms that are constants, or that are integer values. You can really do this a variety of ways. If I get the common denominator of 6 all the way across the board, I'll have a 12 to take place of the 2. The 1/3 would become a 2/6 with a minus in front. The 1/2 would become a 3/6 with the minus in front. 2 negatives make a plus. 4 would be 24/6. A minus and a plus is a minus. 8/3 is 16/6. 2 negatives make a plus again, and 2 would be another 12/6. And if we do all of the addition with all of these numerators, we get 27, right, when all is said and done. And then we could reduce to be 9/2. Now, again, if this was a multiple choice problem, it's very likely that 9/2 will be that choice that you want to circle. In the rare event that this is free response, we would have been completely accepting of that answer, right? That's an unsimplified numeric form. What's nice about simplifying all the answers, all these problems down to their lowest terms, is that especially if you don't have a calculator, you can look to see if it seems reasonable. 9/2 is 4.5. So we're saying that there's about 4.5 blocks that have been shaded in here. And I think if you start counting, you could probably come to the realization that that seems natural. I mean, that's a full block there. Okay, this is kind of estimating, but put those two together, that could make another full block. Maybe it's reasonable to think that these two together make a full block, and then probably all of this stuff is another 1.5 blocks. So it's giving you a way that you can understand that you're certainly in the ballpark. So, okay. Looking to see any questions in the chat. Obviously, this was a little different because you had to find those boundaries on your own, but you know, they don't have to be given to you, basically, is what we're saying. So, all right. We'll go ahead and push on to example 3 with Mr. Meunier.
Heyo. Yeah, example 3 got a lot like example 2, except it has, our dreaded trig functions involved in it. So f of x sine of x, we want to get that graphed. At 0, sine is 0. At pi over 2, sine is 1. 3 pi over 2, it's -1. 2 pi is back to 0. So negative pi over 2 is -1. And negative pi is back to 0, as Mr. Record quickly threw that down. Cosine, remember, always starts up top. We talked about in trig class. So cosine of 0 is 1. It moves down. So from there, pi over 2 would be at 0. Pi is at -1. 3 pi over 2 would be back to 0. And 2 pi is back up at 1. Go the other way, negative pi over 2 would be 0. And negative pi would be at -1. So there is our curves, I should say. And with trigonometry, things repeat themselves forever in both directions. So the regions, we have an infinite number of regions here. So we can kind of find the area of one of the regions, it says, one of the regions. So if we just kind of look from left, we have options. There's 2 on our page right now. Maybe the first one we see on the left has the red curve on top, which is cosine, and the blue curve on bottom, which is our sine. And we need to figure out where are they intersecting each other at? What values are those? So we need to do a little sine equal cosine situation here. A couple of things you can do. You can think to yourself, when does sine equal cosine? You can use that hand trick from trig, or to yourself, where does that happen? Nice drawing. Sine and cosine equal each other at in the first quadrant at pi over 4. I know that because they're both positive there. Or it would be in the third quadrant, which would be either 5 pi over 4 if we think about going around a normal positive angle. And we've talked before how things repeat every 2 pi. So if you subtract 2 pi from that and go a backwards angle, kind of in reverse, 5 pi over 4 would be equivalent to -3 pi over 4. Another way to think of that would be if sine equals cosine, we could divide through by cosine. Yes, Reese, I'm finding the boundaries right now. And if you divide through by cosine, you're going to get sine over cosine is tangent. Tangent equal to 1, and tangent equals 1 at pi over 4, 5 pi over 4, or -3 pi over 4. So we just found our boundaries there. The very first intersection Mr. Record is labeling now is at that -3 pi over 4. The second intersection Mr. Record is labeling at pi over 4. And that 5 pi over 4 would be the third intersection point we see that we didn't really label or use. But there's the third time in this particular picture that these two functions are intersecting each other. Now, if we want to find the yellow region, we could do a definite integral. starting from a boundary of -3 pi over 4, the first intersection point, to a positive pi over 4, our second intersection point, and take the top minus the bottom. And again, using the yellow, our top curve is cosine of x, while our bottom curve is the sine of x. So it had to be a cosine x minus a sine of x dx. And then we would need to integrate that. The integral of cosine is sine. Our integral of sine is a negative cosine, and the negative mixed with the negative sign in front of that makes it a positive sine, or positive cosine, excuse me, yeah, positive cosine, from pi over 4 down to -3 pi over 4. And then who remembers trig values? We plug pi over 4 in, so the sine of pi over 4 plus the cosine of pi over 4. And then we're going to subtract, plug in -3 pi over 4, sine of -3 pi over 4, plus the cosine of -3 pi over 4. And we got to start simplifying. Now, Mr. Record, correct me, if this by some miracle is a free response, isn't that sufficient work?
It certainly would be
Right.
sufficient. Yeah.
Yeah. Now, most likely this not be a free response.
Yeah, that's
So,
probably more likely the case.
mhm. So sine of pi over 4 then, that's going to be radical 2 over 2. And the cosine of pi over 4 is radical 2 over 2. Subtract out, the sine of -3 pi over 4 is negative radical 2 over 2. And the cosine of -3 pi over 4 again is negative radical 2 over 2. So, Mr. Record, we're going to distribute the negative through, it looks like, giving us a radical 2 over 2 plus a radical 2 over 2, plus a radical 2 over 2, plus a radical 2 over 2, which would be 4 radical 2s over 2, which is 2 radical 2.
Yeah, another good example where we're working probably just as hard to simplify our answer once we've performed all the calculus, which is just sometimes it goes with the territory. And that's what we're trying to make you guys comfortable with. You're going to find out as we move deeper into the more difficult problems, applications of area and volume, the focus is going to turn now on just the setup. And sometimes that will happen, you guys. In fact, many of your problems that are planned on your unit exam will just ask you to set up what would the integral expression look like that would depict the particular area. So that's going to be good news. But we still, we're still, excuse me, working out some of our deficiencies with integrating. And I've had a long talk with a lot of my kids how some of the weakest things that we are integrating, the things that we're challenged most with, is sometimes just integrating polynomial expressions like this. It's funny how we're pretty good with e to the x and 1 over x, but the polynomial expressions are what seems to be our Achilles heel right now. So this will give you a chance to kind of work that out a little bit. So,
Hey,
yeah,
Mr. Record,
sure.
should we point out on example 3 how if they would have gone from pi over 4 to 5 pi over 4,
Yeah,
they would still be okay?
Yeah, it's a great idea.
So maybe they didn't maybe they wouldn't work it backwards to get their sketch. I mean, I don't know.
Yeah. In fact, I could
So
pull that. I could pull. How about if I pull it in and just use the calculator to
yeah,
definitely integrate it?
just
Yeah.
how it's the same answer.
Yeah. This is a great point. And Mr. Meunier and I were actually having a conversation about this before we even went on the air today. But if we if we do our integration here and we start at the lower boundary and you see this pi over 4, let's start from there now. So there's so many different ways to type that in. I'm just going to use the division button for that. And now our upper boundary would be this 5 pi over 4 that we just spoke about. And then, of course, we've got our same integral expression, which is the
But now the
oh,
integral is going to be it's going to flip. That's the key
yes,
thing. It's
yeah,
cosine.
yeah. I almost put my foot in my mouth. It's not the same expression. He's right. The blue graph is now on top. And if we hit enter, we do indeed get the same answer. And his conversation and I, the conversation that Mr. Renee and I had, honestly, it probably is a lot more intuitive for students to think about finding the area of this green graph. And that's completely fine. We do know that if you were to check the key, the notes key, um, I had just committed myself to using this part of the graph, and that's the direction that I took. But it by no means is the best way to do this. Some of you might be much more comfortable finding the area of the green shaded region, and that's completely fine. That's completely fine. In fact, Mr. Renee noticed there was a small error in the solution key that I had made, and I'm going to get that reposted here immediately after we go off line here, so that if you guys check it, you won't get confused. It still has the same correct answer, but it's a little bit erroneous in the way that it was set up. So, okay.
Yeah, Mr.
Um,
Record, also on a
mhm.
trig one like this, wouldn't they typically give you some type of boundary to solve it between?
A
Most
lot,
likely.
a lot of times they do, because they're putting a lot on the student's shoulder to remember this trigonometry. And if a student forgets this trigonometry, then they're out of the problem. And it's not the AP trigonometry test, of course, although there are bits of trig that we do need to know. But yeah, we picked a doozy here to kind of close out today, just to kind of get some practice with our trig. Um, I wouldn't worry a whole lot. Our trig is always a work in progress. Mr. Meunier laid a tremendous foundation for it, and we just kind of use the bits and pieces of that trig that he taught that show up most commonly in calculus, and we find ourselves just gradually getting really better and better at that, to the point where it's mastered. So you're going to be fine. You're like no other different group. And then as far as Mr. Meunier's students, it's the trig foundation that was probably laid with Mr. Gatens and Mr. Tierman. So yeah, we're all good. We're all good. So any other questions, I guess, over the 3 problems? Jason had asked one about IUPUI. I want to go ahead and just spend a couple of seconds I can talk about this. I did look online at the results, and we were in like a 7 or an 8-way tie for first. We are now just in a 5-way tie for first, or I'm sorry, 4-way tie for first. So apparently 4 of those schools or so that we were tied with did not receive a 60. A couple of the really big programs in the country failed to get a 60. A few of them got a 59. So what I am going to do is I'm going to post those here later this afternoon on Schoology, so that you can kind of see where we fit in and where the other schools are and so forth, what their names are. We still have 3 students that are tied for first in the nation. And then the other thing that's absolutely fantastic about this is we are not obligated to take the next exam prior to the April 3rd deadline. We have been given permission to administer it whenever, and we can always report the scores at that point and still remain in contention. So none of this having to recruit kids who want to take the CML or to CML to come in over spring break. We're not going to do that. Um, we're pushing you guys pretty hard through these 2 e-learning weeks, and our plan is to let you guys relax for 2 weeks, and then we're just going to see what the world does after that. Neither Mr. Meunier nor I know what's going to happen. We're just taking it day by day, and we'll just, you know, do what we can in the meantime. So, but that's a great question. It's a great question. Um,
I
yeah,
think you're
yeah,
talking about
Jason,
CML.
I
Yeah.
know you had talked about IUPUI. The CML thing came to my mind immediately. So, no, the IUPUI math contest. What's going to happen with that is I've got all your submissions. I've mailed them Friday, and they will email you personally to let you know if there is if indeed you are a possible recipient of an award. Now remember that that awards banquet is April 17th, which could be still during the social distancing time, so they may move it, they may not. We'll just have to stand by with that. And then as far as the points that go into the grade book, I will be working on that very soon this week. I've got them logged in, I just don't have them entered just yet. So yeah, I'm sorry, Jason. I wanted to hit both of the CML IUPUI while it was on my mind. So. All right. Everybody know that you have a skill builder over this topic. 8 point, it's kind of a grouped with the three topics, 8.4, 8.5, and 8.6, I believe. You all can access that from your prospective Schoology page. And obviously it works best if you can print it out, but if you can't print it, you can certainly pull it up on your computer screen, and then you can just do your work on a separate sheet of paper. And Mr. Meunier and I are going to get together and decide if we may end up putting this together as another Schoology submission that would be awarded for completion, but it's just a way to make sure that you guys are keeping up with things and so forth.
Yeah,
And
I
mhm.
got no ideas for that. I'm kicking around. I think I'll have something for that this afternoon to show you, Mr. Record, maybe.
Perfect, perfect. And then, stand by, you guys, for the potential quiz that would cover 8.4, 8.5, 8.6, these ideas with areas, because we had one that was going to be planned for in class, so we can just adapt it to be used for Schoology. So, all right, we are postponing any CML practice at this point. I feel like you guys have enough to worry about. We'll discuss that definitely towards the end of the week, how we're going to implement that. Hopefully we get more information about what our timeline is going to be by the end of each of our weeks coming up. So, all right, if that takes care of all your questions, I think Mr. Meunier and I are going to skedaddle and get focused on our other classes. We thank you guys. You're the ones that are doing what you're supposed to do. We really appreciate seeing you guys in the live feed. Um, you know, our view count for the recorded is pretty strong. It's still a little shy of the total numbers of students that we have, but we do understand that we have few people that are kind of working together, um, which is fine, I guess. I mean, it kind of violates this whole social distancing thing, but we're not going to judge, of course. But it's just really important that you guys make sure that you keep up, because you've worked too hard to let something like this drag you back days or weeks, because our hope is, being eternally optimists, that we get back to school, things return to normal, and you guys take that AP Calc exam, and you know what? Guess what? A lot of the world's going to have a hard time with that, because a lot of the United States, the e-learning thing is not a go. Teachers don't know how to do it. We're very fortunate that Avon took the lead with this, and we feel like we have a halfway decent handle on it. So let's let the Avon kids do well. We'll raise that curve, and we'll be the ones that are looking good, when the scores come back. So, all right. We do not know about Avon taking the late AP testing dates at this point. I think so much of that does revolve around the date that we are coming back to school. I know I can't speak for all of the other disciplines, but Mr. Meunier and I are in really good shape with calculus, we thought. We've been very thorough, more thorough than any year that we've ever taught. He and I talk about this every day, how we just are so much more thorough, which means that our review time doesn't have to be quite as encompassing. But yet we did have a very broad review laid down that was going to address some of the weaknesses that we thought we saw with you guys. So as of now, we don't think Avon's going to be taking the late test dates, but that could change. So we're focusing right now. May 5th is our test date, and we're going to be in good shape. We're going to be in good shape, you guys, but we'll always keep you posted. So, all right. So we'll see you tomorrow. We're going to do a couple of more examples from topic 8.5, I believe, but we'll get that link posted tonight. In the meantime, you guys do your quiz and have that submitted by 11:59 tonight. And then please, by all means, you can start working on the homework that we just assigned. I think you're just doing the first 6 problems. So please email either Mr. Meunier or myself if you have any questions. We have nothing else to do, right? So we'll certainly get back to you. So Mr. Meunier, anything else to add?
Nope.
All right.
Looks good. Good luck out there.
All right, guys, have a great day, and we'll see you tomorrow.